Hello, everyone. So this is the next module on our list of hydrocarbon modules, which is naming alkanes. So previously, what we had was an introduction on what alkanes are, their properties, and what makes them stand out, or what are the unique characteristics of alkanes. This time, for this module, what we will have would be how do we name these alkanes? Because, of course, there are variations, and how did we arrive at those names that are very popular and you see in the industry, in reference materials, etc. So this is all about nomenclature. But of course, before going straight to how do we name the alkanes, let's go to some concepts that we previously encountered. So of course, we talk about alkanes. These are still hydrocarbons with carbon and hydrogen bonds. And there are two types or two classifications. We have acyclic alkanes and we have the cycloalkanes. So let's just go through them one by one. Acyclic alkanes has the formula, this one. This is the generic formula of acyclic, meaning the bonds between carbon and hydrogen are just linear, or they are just single bonds. Okay, this is how they usually look like. Okay, it's a single bond, no double bond in the structure of the compound. So it follows again that formula C sub N H 2 sub N plus 2. What dictates the hydrocarbon would be the number of carbon. So if this is 4, then we can compute that. That's 2 times 4 plus 2. So that's 10 already, because that's 8 plus 2. Therefore, if we're using a 4-carbon alkane, then there should be 10 hydrogen atoms following this formula. And then that becomes an acyclic alkane. But still, the bonds are single bonds. Okay, let's also consider saturated hydrocarbons. They're called saturated hydrocarbons when they have the maximum number of hydrogen atoms per carbon. Okay, of course, a hydrocarbon would really be a combination of hydrogen and carbon atoms. And of course, our carbon, having a valence electron of 4, can accommodate 4 bonds. And it's called a saturated hydrocarbon when all of those slots or those valence electrons are filled out and they use up the maximum number of hydrogen. Then the second one will be a cycloalkane, which is different from acyclic because the carbons join in one or more rings. Molecular formula is different also because it's just CN2N, meaning there are less hydrogen atoms in this type of alkane. So they have fewer H atoms than acyclic alkane with the same number of carbons. So again, two types, acyclic and cycloalkanes. Okay. Okay, when you talk about structure, so let's just go through some representations of your alkanes pictorially. So all carbon atoms in an alkane are surrounded by 4 groups. This is sp3 hybridized. If we go to the 1s2, okay, but we don't go there. We just want to really see the structure of these alkanes. So tetrahedral, most of the time in the ball and stick model, you would want to identify the angle between the bonds. So let's see, for example, for methane, which is CH4, Lewis structure, very simple. It only tells you of course, the unit structure of the compound. So this is it in Lewis structure, 3D. This is how it looks like. And in a ball and stick model, which is the pictorial, will be this way. And of course, the bond angles are always at 109.5 degrees. So just take note of that. So that's usually the bond angle, meaning how the hydrogen atoms are connected to your carbon, the angle they're connected. So again, this is Lewis structure, 3D representation, and this is the ball and stick model. Specifically for a ball and stick model, you take care of the 1.09.5 degrees angle. Okay, for CH3, or this can also be C2H6 if we are considering a cyclic alkane. So this is how it looks like, 2 carbon atoms and 6 hydrogen atoms, 3D. And for propane, CH3, CH2, CH3. So this is how it looks like. You can also consider propane as 1, 2, 3. So that is C3H8. Okay, ethane is C2H6. Methane is CH4. In hierarchy, that is how they are arranged. Okay, let's have the next one. In propane and higher molecular weight alkanes, the carbon skeleton can be drawn in a variety of ways and still represent the same molecule. Yeah, and the molecule of a compound, irregardless if you bend them, for example, a bend in the chain doesn't really matter as long as the number of atoms are met. For example, for propane, which is C3H6, there are 3 carbon atoms. They can be drawn this way, like straightforward. Or if a bend is required, for example, when you're drawing the figure, that's okay. It says again, the bends in a carbon chain do not really matter. But for example, you're using 4 carbons. So how can you arrange them? So it says here there are 2 different ways to arrange 4 carbons, giving 2 compounds with molecular formula C4H10. This again follows the formula C sub n, 2 sub n plus 2. Okay. So for example here, you can use this one because you're using 4 carbon atoms. So 1, 2, 3, 4. So this is how you can arrange them. This is a straight chain alkane, whereas the other one uses a branch chain alkane, but still have the same number of carbon and hydrogen atoms in the molecule. So this is 1, 2, 3, 4. And for example, for the hydrogen, you still need to meet the 10 hydrogen atom requirement. So that's 3, 6, 9, 10. So this is a straight chain alkane, and this is branch chain alkane. Butane and isobutane in this case are constitutional isomers. This when you talk about constitutional isomers, these are different compounds, but with the same molecular formula. Constitutional isomers differ in the way the atoms are connected to each other. It's the only difference. When it's a constitutional isomer, it has the same molecular formula, but the compound is entirely different. But of course, that follows that the way the atoms are connected will also be different. Carbon atoms and alkanes and other organic compounds are classified by the number of other carbon directly bonded to them. For example, a primary carbon is bonded to one other C atom. A secondary carbon is bonded to 2 other C atoms. A tertiary carbon is bonded to 3 other C atoms, and so forth, so on and so forth. For example, a quaternary carbon is bonded to 4 other C atoms. So this is how. So this is a primary carbon. This is a secondary carbon, a tertiary carbon, a quaternary carbon. And if we, of course, mix them all up together, connect them, this one is connected to only one other C atom. So it's connected there. But these are 2. So they can connect to 2 other C atom. So this is 3, and it's connected to 3 also. And 4, it's also connected to 4 other C atoms. But technically, it's a primary carbon when it's only bonded to 1 other carbon atom, secondary, tertiary, and quaternary. Hydrogen atoms are classified also as primary, secondary, or tertiary depending on the type of carbon atom to which they are bonded. So, as always, your reference atom is the carbon atom. And if your carbon atom is primary, then correspondingly, its hydrogen atoms are also primary. So, a primary hydrogen is on a C bonded to 1 other C atom. So, what dictates the classification of hydrogen would be the classification of its carbon atom. For example, here, this is a primary carbon. Therefore, the H that attaches to it, it's also a primary hydrogen atom. This is a secondary carbon. Therefore, what attaches to it is a secondary hydrogen. And for example, this is tertiary, and this is a 3 classification of tertiary hydrogen atom. So connecting them all up, so this is where you would find your primary hydrogen, your secondary hydrogen, and your tertiary hydrogen. The maximum number of possible constitutional isomers increases dramatically as the number of carbon atoms in the alkane increases. So there are 75 possible isomers for 10 carbons and 366,319 possible isomers for 20 carbons. The suffix A and E identifies a molecule as an alkane. We know that already. Of course, there is alkenes and alkynes, but we are very bound to alkane at this moment. So by increasing the number of carbons in an alkane by a CH2 group, which is methylene, one obtained a homologous series of alkanes. But just take note of those distinct characteristics of alkanes. Alkanes are hydrocarbons having single bonds of carbon and hydrogen. And these are all just more information related to this type of hydrocarbon. So I believe you've seen this before. So these are in hierarchy, how they are named: methane, ethane, propane, butane, pentane, hexane. Again, you would see this, the prefix follow the number of carbon in the chain. Okay. So for example, pentane, this one, it doesn't use those yet, but for pentane, that's 5, hexane 6, heptane 7, octane 8, nonane 9, decene 10, and eicosane is 20. And possible number of constitutional isomers would be the following. Okay. Okay, now let's go to the next slide. Okay, I'll be skipping the following. I'll go straight to naming because you've seen this a while ago. Okay. It's just always lowest structure, and then you could also use 3D pictorial or the stick and ball model. So when talk about nomenclature or naming, this is how those names are derived. So the name of every organic molecule always has 3 parts. The first will be the parent name, indicating the number of carbons in the longest continuous chain. The suffix indicates what functional group is present. And of course, the prefix tells us the identity, location, and number of substituents attached to the carbon chain. So this is how it usually is. So this is like a guideline on how those alkenes or these alkenes are named. We have a prefix, we have a parent, and we have a suffix. The prefix tells you what and where are the substituents. And then parent, this is the longest chain of carbon. And this is the functional group for the suffix. For example, in this case, Carbon substituents bonded to a long carbon chain are called alkyl groups. An alkyl group is formed by removing one H atom from an alkane. Okay, it's a substituent, meaning it's not getting the same complete formula as its original parent chain. So you're removing one H atom from an alkane. To name an alkyl group, all you have to do is drop the A and E and change it to YL. For example, methane, drop one hydrogen, that becomes CH3. Therefore, this becomes methyl. For ethyl, ethane, for example, this is CH6. C2H6, I'm sorry. So you drop one, it becomes C2H5. Therefore, your ethane becomes ethyl. Naming 3 or 4 carbon alkyl groups is more complicated because the parent hydrocarbons have more than one type of hydrogen atom. Exactly. That is where the complicated naming starts. Propane has both primary and secondary hydrogen atoms, and removal of each of these H atoms forms a different alkyl group, a different name. For example, this one, see, these are primary hydrogen. Removing one, of course, that becomes a propyl group. But this time, for example, what about removing two? Because a secondary hydrogen atom, meaning there are two bonds possible. So if you remove two hydrogen, that propyl becomes isopropyl. For now, I think it's just best to remember the different structure and the name associated with the structure. You can always go back anyway to the presentation. Okay, so how do we do that? Find the parent carbon chain and add the suffix. So for example, this one. 1, 2, 3, 4, 5, 6, 7, 8. So these are the 8 atoms in the longest chain. Meaning, identify, since 8 is the longest chain, then that's an octane. And for example, this is not actually is this the longest chain? So this is not the longest chain because 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. That is actually the longest chain. Because it doesn't matter if the chain is straight or even if it bends, you would still look for the longest chain. So in this case, this is not the longest chain. This is the longest chain. That's just how to identify the longest chain. For example, we look for the longest chain. This is the longest chain. In this case, this is the longest chain. And for example, this case, so this is also the longest chain. It only bended. I mean, the structure only bended, but still, the chain of C's are still, this is still the longest one. Okay? If there are two chains of equal length, pick the chain with greater number of substituents. For example, you have this chain. We've identified, and then there's a substituent, meaning connecting or branching out. So that's 1, 2. So this is 7 atoms in the longest chain, but plus 2 substituents. This time, let's see. So this is the longest chain. However, there's only 1 substituent. So what do? We consider this as, we will have to pick this because it has more substituents. Okay. Number the atoms in the carbon chain to give the first substituent the lowest number. So you always start the numbering here. 1, 2, 3, 4, 5, 6, 7, 8. And then the first substituent is at 2. And then the next substituent is at 5. The next substituent is at 6. And this is not how we number it. We always number it from left to right. Okay, this is not how you number it. So this is incorrect. If the first substituent is the same distance from both ends, number the chain to give the second substituent the lower number. Okay, let's see this. So the longest chain, Numbering is always left to right. So 1, 2, 3, 4, 5, 6. The CH3 groups at C2, C3, and C5. And since this has the lowest number of carbon, so this one has, we can identify as, okay, we always give the lower number to the second substituent. Okay, let's see this one. 1, 2, 3, 4, 5, 6. We have substituents. This is incorrect. Why? This is at the onset already incorrect because the numbering was done from right to left. We would always use numbering from left to right. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3 substituents. And then the one with the lowest would always be the second substituent. When numbering a carbon chain results in the same numbers from either end of the chain, assign the lower number alphabetically to the first substituent. So this is how you do it. Two different groups equidistant to the ends. Yes. Yeah. Meaning even if you start from right to left or left to right, they have the same distance from the edges. So this is the third, ethyl at C3, methyl at C5. Earlier letter means the lower number. Okay. We would still have to follow the lower number. And then name and number the substituents. Name the substituents as alkyl groups. Every carbon belongs to either the longest chain or a substituent, not both. Each substituent needs its own number. If two or more identical substituents are bonded to the longest chain, use prefixes to indicate how many. Di for 2, tri for 3, tetra for 4, and so forth. So the longest chain here is 1, 2, 3, 4, 5, 6, 7, 8. Substituents will be at 2, will be at 5, at 6, and at 8. So if you want to rename them, it's methyl at C2, ethyl at C5, and methyl again at C6. So this is the lowest number in the chain, but that's why it's both methyl, 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 and then ethyl will be the one with 2 additional carbon in the link. This molecule has 3 substituents bonded to the longest carbon chain. And then, of course, combine substituents and numbers plus parent and suffix. Precede the name of the parent by the names of the substituents. Alphabetize the names of the substituents, ignoring all prefixes except ISO, as in isobutyl and isobutyl. Precede the name of each substituent by the number that indicates its location, and separate numbers by commas and separate numbers from letters by hyphens. Again, take note. Numbers are separated by commas and separate numbers from letters by hyphens. A letter number separation is using a hyphen. The name of an alkane is a single word with no space after hyphens and commas. So let's see. Longest chain. Then let's check the substituents. We have 1 at C2. We have at C5. We have C6. And the whole chain, of course, the parent chain is 8 or octane. Therefore, if we're naming it, we said that separate numbers by commas. This chain has 2 methyl substituent. Therefore, that's 2,6-dimethyl because of 2. And then their positions are at 2 and 6. And then we also have a 5-ethyl here because its position is 5 and that name is ethyl. Okay, putting them all up together. Okay, this is 5-ethyl, 2,6-dimethyl, and then the parent has 8 C's plus oct and then A. Therefore, the whole name of this chain is 5-ethyl, 2,6-dimethyl octane. You start with the substituents and then the parent. The substituents should be named specifically. So that's 5-ethyl, dimethyl octane. And then, but for cycloalkanes, it's different. Cycloalkanes are named by using similar rules, but the prefix cyclo immediately precedes the name of the parent. So in the previous example, for a cyclic, meaning single bonded alkanes, all you have to do is, of course, get the prefix and then attach A and E. But this time, we have to carry over cyclo in naming the molecule. So again, prefix plus cyclo plus parent plus suffix. So let's check. First, find the parent cycloalkane. So there are how many C's? So 1, 2, 3. But it's a ring form. It's a ring structure, so there are 6 C's in the ring, and therefore it's called a cyclohexane. But as I've said, I think earlier during our class, we said that we won't be focusing on cycloalkanes, only acyclic alkanes. But of course, it's already here, so we get to know them also. Name and number the substituents. No number is needed to indicate the location of a single substituent. So this is a methyl cyclohexane. This is a tert buty cyclopentane. For rings with more than one substituent, begin numbering at one substituent and proceed around the ring to give the second substituent the lowest number. So you always count clockwise. So that's 1, 2, 3, 4, 5, 6. Okay, numbering counterclockwise is incorrect. So you always number clockwise. So CH3 groups at C1 and C3, those are the substituents. Again, this is ring. And we normally don't see it from the given examples we had before. So the substituents are at position 1, position 3. So that's 1, 3, dimethyl cyclohexane. With 2 different substituents, number the ring to assign the lower number to the substituents alphabetically. So this is begin numbering at the ethyl group because that's the lowest. Okay. And then it's ethyl at position C1, and then it's methyl at position C3. The earlier letter would always have the lower number. Therefore, this is 1 ethyl, 3 methyl cyclohexane. In the case of an alkane composed of both a ring and a long chain, if the number of carbons in the ring is greater than or equal to the number of carbons in the longest chain, the compound is named a cycloalkane. But of course, again, I would repeat it. We really don't need to know this in detail, just passing through, because we are always only concerned with acyclic alkanes. And then this is an example of rings and chains. So this is in contrast. This is a ring with a chain. So this is 6 C's in a ring. It's called cyclohexane. And then 6 C's in the ring is a cyclobutyl group. Okay. These are also other formations. No number is needed with only one substituent, so no need. So just straight out, this is an ethyl cyclobutane. Assign the lower number to the first substituent alphabetically, the B of butyl before the M of methyl. So that's 1 cyc-butyl, 3 methyl cyclohexane. Number to give the second CH group, the lower number 1, 2, not 1, 6. And this is number to give the second CH3, CH2 group, the lower number. Okay. So some physical properties of alkanes. Alkanes have low boiling points compared to more polar compounds of comparable size, meaning they boil faster at lower temperatures. So they can boil easier. So for example, this one. increasing the strength of intermolecular forces, increasing boiling point. Boiling point increases as the number of carbons increases because of increased surface area. I believe I've said that before. And the more number of carbons present, the increase, the bigger or the higher the boiling point. Okay. Some other properties of alkanes. The boiling point of isomers decreases with branching because of decreased surface area. But when it comes to melting point, increasing strength of intermolecular forces also increasing melting point. It says that alkanes have low melting points compared to more polar compounds of comparable sizes. Melting point increases as the number of carbons increases because of increased surface area. Melting point increases with increased symmetry. For solubility, alkanes are soluble in organic solvents and they are insoluble in water. I think that was highlighted before. These alkanes need special solvents to dissolve in them. Water cannot dissolve your alkane. Is that my last slide? Lastly, last few slides. So examples are fossil fuels where hydrocarbons are present. Many alkanes occur in nature, primarily in natural gas and petroleum. Natural gas is composed largely of methane, but lesser amounts of ethane, propane, and butane. So if you would look at that description alone, you can see that this is a direct application of your alkane. Your alkanes are present in fossil fuels. Petroleum is a complex mixture of compounds, most of which are hydrocarbons, containing 1 to 40 carbon atoms. Distilling crude petroleum separates it into usable fractions that differ in boiling point. So some examples of your petroleum would be gasoline, kerosene, or diesel fuels with these as their molecular formula. So if you would see, these are chains of carbon and hydrogen. So for example, taking a barrel of crude oil, this is probably how it would look like, okay? And this is basically one big application of your hydrocarbons will be in the fuel industry or in the petroleum industry. Okay. And for now, that's it. I just wanted really to guide you on how to name your hydrocarbons. And this is the simplest guide I can find. So I hope you learn something and you can apply it in your different modules. And should there be a question, this reference will also be shared to the group later on. Okay, so thank you so much. Please do me a favor and subscribe to the channel so that you'll be updated every time there's a new video. Thank you so much and good day, everyone.